Okay, so let's talk about the type of energy changes that will actually take place when an ionic compound is being formed. Now, if you look at the simple description that we gave earlier, where the sodium loses an electron and the chlorine gains an electron, and you end up with sodium chloride. Well, energetically speaking, that is not giving the total picture because, and we can tell that by looking at some data. If you look at this here, you'll see that the ionization energy for sodium, the first ionization energy for sodium is given here, 496 kilojoules per mole, while the electron affinity for the chlorine is minus 349 kilojoules per mole, right? Now, if you simply add these two together to get the overall equation for the formation of sodium chloride, then you'll notice that when you add these two numbers, you're going to get a positive result. Um, that would indicate that the formation of sodium chloride is not feasible and would not be stable, which we know, of course, is not true. Sodium chloride is very stable. So, just looking at the electrons being lost and gained and the energy changes taking place in that process um, by itself is not enough to explain why is it that sodium chloride and other ionic compounds are stable. What we have to look at is what is known as the enthalpy of formation, which we talked about before, I believe in chapter 6. And you will see that the enthalpy of formation is actually more important than either of these energies here. In fact, in order for us to get a true picture of the energy changes taking place, we have to use what is called a Born-Haber cycle. Let me go to full screen here. And let me skip all this since I discussed this already. So, yes, so Born-Haber cycle is what we're going to look at in order to understand why is it that sodium chloride and other ionic compounds turn out to be energetically stable. Um, so the Born-Haber cycle is basically a hypothetical process which represents the enthalpy of formation in several steps. So it's not a one-step process to go from the elements to the final product. All right. There are several steps, as you can see in this diagram right here. So basically, if we start here with sodium in a solid state and chlorine in a gaseous state, going from here to the product, right, the enthalpy change for that would be, by definition, the enthalpy of formation, and that turns out to be minus 411 kilojoules. All right. Now, what we're going to see is how do we get from the start to the end through the steps shown here. But before we do that, a very important question is being asked here. It says, what law can be used to find the enthalpy change that occurs in steps? And the answer, of course, would be Hess's law, right? Hess's law, because if you remember, Hess's law states that it doesn't matter how you get from the reactants to the products, be it through one step or more than one steps, the enthalpy change would be the same. So what that means is that going from here to here, going from the reactants to the product in one step, which is not what actually happens, but hypothetically speaking, then the enthalpy change for going from here to here is the same as going through all these steps, 1 through 5, to get to your final product. All right. Okay. So with that said, let's proceed. So we're starting from sodium and chlorine here. And you'll notice that the first step involves converting sodium in a solid state to sodium in a gaseous state, right? And by definition, going from the solid state to the gaseous state, that's called sublimation, all right? So the enthalpy change that is required for that is called the enthalpy of sublimation. And then going from, so therefore, that's how we end up with sodium in a gaseous state. And let me backtrack a bit here. I accidentally clicked. Okay, enthalpy change of sublimation, the enthalpy of sublimation is given by 107 kilojoules. Okay, then we get to going from here to here, step 2. And you'll notice that what is happening here is that the chlorine molecule is converted to chlorine atoms. So basically what you're doing is breaking up the chlorine molecule. You're busting the bond between the two atoms to form the chlorine gas. So we call that enthalpy of atomization. All right? You're converting the molecules to atoms. And in the case of chlorine, that value is equal to 122 kilojoules. All right? Then we have a situation where the sodium in a gaseous state loses an electron to form sodium gaseous ions. And that, of course, is called the ionization energy, which for sodium is equal to 496 kilojoules. All right. And then, well, before we get to the next step, I want to highlight at this point is that the first three steps that we discussed here are endothermic steps. In other words, energy is required in each of these cases, right? Energy is required to convert the solid sodium to the gaseous sodium. Energy is required to break the chlorine to chlorine bond to form chlorine atoms. And energy is required to remove an electron from the gaseous sodium to form the gaseous sodium ions. So these first three steps are endothermic. So the next step is where you have the chlorine atom gaining the electron to form the chloride ion. And that, of course, is electron affinity, for which the value for which, in the case of sodium, is minus 349 kilojoules. And of course, that is an exothermic process because the electron affinity is always negative. So that's why you have the arrow pointing down now. So now we get to the very last step. And the last step is where we have the combination of the sodium ions with the chloride ions to form sodium chloride solid. And that is called the lattice energy. Now, there seems to be some confusion in the literature as to what the actual definition of lattice energy is, because in some textbooks, the lattice energy is defined as the energy required to break up the sodium chloride or any ionic compound into its gaseous ions. In other textbooks, they define the lattice energy as the reverse. The energy that is the energy change that takes place when the gaseous ions combine to form the sodium chloride solid. So what I'm going to do is I'm going to refer to your textbook. If I can go to Canvas here and see what your textbook says. And we're just going to stick to that definition. So let me go to the text, OpenStax text. And let me go to, now this will take some time. I should have done this before. I apologize. In the meantime, let me go back to this here and say a couple more things about this here. So go back to the Born-Haber cycle. Okay, now if we're assuming that the lattice energy by definition is the energy change taking place when the ions combine to form the solid ionic compound, what you'll see here is that this value here is very negative, right? In fact, it's the most negative value in this series, in this cycle. And that is a reflection of how stable the sodium chloride is. And in fact, it is because of this relatively large negative value that the enthalpy of formation for sodium chloride is negative as well, all right? Which again supports the fact that the sodium chloride is a stable compound like any other ionic compound. Okay, so let me get out of this and go back to, oh, it's still downloading. Okay, so let me get back to the PowerPoint here. And what I'm going to do in the meantime, as inconvenient as it is, I'm going to move on to the example that's on the next slide. All right, so here is an example of a Born-Haber cycle type problem. It says use the following data to determine the lattice energy of magnesium fluoride. The enthalpy of sublimation of magnesium is, and it gives you, in fact, it just gives you some values for the sublimation of magnesium, the first ionization energy and the second ionization energy of magnesium, the bond dissociation energy of fluorine, the electron affinity of the fluorine atom, and the enthalpy of formation of magnesium fluoride. All right. Okay. So what I've done here is that I copied and pasted this onto this here so that I can have more space to solve this problem. So what I'm going to do is make this larger so that you can see what's happening here, so that I'll have enough space to Okay, so that I can have enough space to do my work. Okay, so basically, let me start from here. Basically, we want to look at getting from, okay, how shall I do this? Getting from magnesium solid. Okay, now I don't like the look of that. So let me reduce the ink flow. So magnesium solid and F2 gas to form MgF2 solid. And for this, we need the enthalpy of formation, which according to the information provided, that is equal to minus 1124 kilojoules. All right. Okay, so magnesium, let's start off with that first. And the first step would be the conversion of magnesium from magnesium solid to magnesium gas. Whoops. And the energy required for that would be the enthalpy of sublimation, which according to the information here is plus 146 kilojoules. So this would be plus 146 kilojoules. And then now, in the case of fluorine, we're going to convert fluorine molecules to fluorine gas. And according to the information here, the bond dissociation of fluorine, the energy required for bond dissociation is 159 kilojoules. So this would be plus 159 kilojoules. Then the next step would be where the magnesium loses an electron. Actually, it will lose 2 electrons. So basically, you're going to go from here to Mg2 plus. And the energy required for that would be the sum of the first and the second ionization energy. So basically, this would be, let me see here, the first ionization energy is, okay, I lost my place. Okay, it would be 738 kilojoules plus 1451 kilojoules, all right? And then now for the 2 fluorine atoms, to get 2 electrons that have been lost by the magnesium, for that you're going to need the electron affinity, which for one fluorine is minus 328 kilojoules per mole, or just kilojoules. But we have to multiply that by 2 because there are 2 fluorine atoms, all right, to get the 2 fluoride ions. And then to get from here to here, we need what is known as the lattice energy, which is what the question is asking for. So let me go back now to here to see if, okay, the textbook should have been downloaded by now. Okay, so what I'm going to do is search for the definition of lattice energy according to your text, and we're just going to stick to that. I think that would be found, let me see here, chemical bonds. What was it? Okay, let me scroll down. Looking for the Born-Haber cycle. Okay, so let me see here, lattice energy. Let me see if it defines the lattice energy here. Okay, so here's the definition of the lattice energy. So according to your textbook, the lattice energy is the energy required to separate a mole of the solid into its component gaseous ions. So basically, you're starting from the solid ionic compound to form the ions. The energy required for that would be the lattice energy. So based on that definition, going back to the problem, that means that the lattice energy is actually the energy required to go in this direction. So that would be delta H lattice energy, all right? So what that means, therefore, let me scratch this out here. In fact, let me be neat about it and erase this here. Okay, So go back to my pencil function. All right. So um, so basically what the question is asking for you to do is calculate this delta H lat, all right, or the lattice energy. All right. Now based on that, we can set up a mathematical relationship. So if you look at this carefully, going from here, going from, whoops, going from this plus this to give you this, and then going from this to here is the same thing as going this route right here. So in other words, I can start off with minus 1124 kilojoules plus delta H lattice energy is equal to plus 146 kilojoules plus 159 kilojoules plus 738 kilojoules plus 1451 kilojoules plus 2 times minus 328 kilojoules, and that's it. And basically it's all math from here. All you have to do is use your calculator to do your number crunching. So let me do that now. So on the right side of the equation, let me work that out first. That's 146 plus 159 plus 738 plus 1451 plus 2 times minus 328, and that works out to be 1838 down here, 1838 kilojoules. So that means that delta H lat is equal to 1838 kilojoules plus 1124 kilojoules, and let me do that here, plus 1124. Okay, so according to my calculations, this works out to be equal to 2962 kilojoules. Oops. Kilojoules. And that's basically how that is done. All right. So this is a typical lattice energy Born-Haber cycle type problem. All right. Okay. So what else? Let me go back to the PowerPoint. Okay. So the next topic, we'll be looking at Lewis structures of simple molecules. All right. So until next time.